Welcome back. In this lecture video, we're going to be looking at fixed effects versus random effects in the context of the completely randomized design. Now let's first look at fixed treatment effects. If the treatments used in the experiment constitute all of the treatments of interest to the experimenter, then the effects of those treatments are constants, also known as fixed effects, in the statistical model. The focus of hypothesis test involving the treatments will be to determine whether differences exist in the means of the fixed populations. In other words, whether any of the fixed effects of the treatments are non-zero. The focus of estimation involving the treatments will be on estimating the means of the fixed populations and the differences between them. That is, estimating the fixed treatment effects and differences between them. Now, some examples of fixed treatment effects. Suppose that an agricultural extension researcher selects 3 particular varieties of corn to use in an on-farm field trial. The purpose is to determine whether any of the varieties is best on that farm. Now, no other varieties of corn are of interest to the extension researcher nor to the farm owner, and so in this context, corn variety would be a fixed effect. For another example, suppose that a plant manager is interested in comparing the productivity of the plant's 5 machine operators in using a new machine. There are currently no other operators employed by the plant, so these are the only operators of interest to the manager. And so again, in this context, the operator would be a fixed effect. Now let's look at random treatment effects. If the treatments used in the experiment are a subset of a larger population of treatments of interest to the experimenter, the actual treatments used in the experiment having been randomly selected from the population of treatments, then the effects of those treatments are random variables, also known as random effects, in the statistical model. The focus of hypothesis test involving the treatments will be to determine whether variation exists among the means of all treatments in the population of treatments. The focus of estimation involving the treatments will be on estimating the variability among all treatments in the population. Now let's look at a few examples of random treatment effects. An extension researcher randomly selects 3 varieties of corn from a larger population of corn varieties to use in a field trial. The researcher is interested in drawing inferences that apply across the entire population of corn varieties, not just the 3 that were picked for the study. And so in this context, corn variety would be a random effect rather than a fixed effect. As another example, a plant has purchased a new automated machine, and the plant manager is interested in determining whether variation exists in productivity using this machine among the plant's machine operators. Now, suppose that this plant has 100 machine operators, too many to involve all of them in an experiment, so the plant manager randomly selects 5 machine operators to participate in the study. The manager is interested in drawing inferences that apply to the population of all 100 machine operators employed by the plant based on the results from the 5 operators that participate in the study. And so in this context, operator would be a random effect. Now let's look at the statistical models for a fixed effects model and a random effects model. We'll start looking at the fixed effects model. So a fixed effects model in a completely randomized design is given by this model here. So y sub ij being equal to mu plus alpha sub I plus epsilon I sub j, I going from 1 up to the number of treatments, j going from 1 up to the number of replications for a particular treatment. And so in this case, y sub ij is the measured response on the jth experimental unit receiving fixed treatment I. Mu is the overall population mean response across all treatments in the experiment. Alpha sub I is the fixed effect of treatment I, and because these fixed effects are measured as deviations from the overall population mean response, they add up to 0. And then finally, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I, and these error terms have mean 0 and a variance which we will denote by sigma squared, and the error terms are assumed to be normally distributed. Now the random effects model looks pretty much the same, doesn't it? We have y sub ij being equal to mu plus alpha sub I plus epsilon sub ij. So if I scroll back to the previous model, we see that from the standpoint of the mathematical expression, it's the exact same model, or at least it looks exactly the same. Okay, but the difference is in the nature of alpha. Again, y sub ij is the measured response on the jth experimental unit receiving, in this case, random treatment I. In the previous model, in the fixed effects model, the treatment was a fixed effect, but in this case, it is a random effect. Again, mu is the overall population mean response across all treatments in the population of treatments. The big difference is in alpha sub I. Alpha sub I is the random effect. It's a random variable, so it's a random effect associated with treatment I. And the alphas in this case, because they're random variables, the model is such that these have a mean of 0. And because they're random variables, they also have a variance. And we're going to denote the variance of these random effects by sigma squared sub tau, all right, tau for treatment. And when we need to make inferences, we will assume that these random effects are normally distributed. Now, once again, epsilon sub ij is the random error associated with the jth experimental unit receiving, in this case, random treatment I. And again, the error terms have a mean of 0 and a variance which we will denote by sigma squared, and these error terms are assumed to be normally distributed. Now, one additional assumption that goes along with this random effects model is that the random effects for the treatments and the random error terms are assumed to be stochastically independent. So those are the differences between the two models, the fixed effects model and the random effects model. In the fixed effects model, the alphas are assumed to be constants, unknown constants that need to be estimated. All right, they are fixed treatment effects. On the other hand, in the random effects model, the alphas are random variables, also known as random effects. The alphas have a mean of 0 and a variance equal to sigma tau squared. All right, and so that is the big difference between these two types of models. Now let's talk about the statistical analysis for these two types of models. The calculations for the analysis of variance, the good thing is that the calculations are the same for the random effects model as they are for the fixed effects model. So what you've learned up to this point about how to do an analysis of variance for a fixed effects completely randomized design will apply to a random effects model in the context of a completely randomized design as well. However, the specific hypotheses being tested by the ANOVA F-tests are different for the random effects model than they are for the fixed effects model. Now, that's nothing to be concerned about. It doesn't really complicate anything. It's necessarily the case because the parameters of the random effects model are different than the parameters of the fixed effects model. So that's just a byproduct of the fact that the two models have different sets of parameters. So, but having said that, the type of question addressed by the random effects model ANOVA F-test is similar to the question addressed by the fixed effects model ANOVA F-test. So if we think about the kind of hypotheses that we test when we're performing an ANOVA in the context of a fixed effects completely randomized design, we can answer the same type of question if we have a random effects model as well. And so let's let's just take a look at this. So the differences would be the following. The question is expressed in terms of different parameters. Okay, so that's necessarily the case because again, the parameters for the fixed effects model and the random effects model are different. The alphas are constants in the fixed effects model, and they are random variables in the random effects model. So the parameters associated, the parameter associated with the alphas in the random effects model is the variance of that random effect. The inference for the random effects model, ANOVA F-test, is to a broader set of treatments than the inference based on the fixed effects model ANOVA F-test is. And so again, what does that mean? Well, when we do a fixed effects analysis of variance, the inference that we draw applies to that set of treatments alone. All right, and so we can think of that as, kind of a narrower inference space than is the case when we're dealing with a random effect. When we have a random effect and we're testing the ANOVA F-test, or performing testing the hypotheses that are performed by that ANOVA F-test, we are drawing an inference to the entire population of treatments in that population, not just the treatments that were selected for inclusion in the experiment. And so in that sense, the inferences that we are drawing when we use a random effects model is broader than the inference that we draw when we're doing a fixed effects analysis of variance. Now, this can be seen by looking at the expected mean squares for the two types of models. And what are we talking about? The fact that the hypotheses are a little bit, the hypotheses are different in terms of how they are, in terms of what they represent from the standpoint of parameters. But again, let me just reiterate that they're answering the same type of question. And so we'll see that when we look at examples. Okay, so this table, it looks kind of like an ANOVA table, but it's related, but it's a little bit different because, again, notice that we don't have like an F column here. All right, what this table gives us is the rows for the source of variation for a completely randomized design where it's the decomposition of the total amount of variability. We've not included the total variability here because we don't need it. We're not calculating any kind of expected mean squares based on that. So we only need these two rows. So these two rows, again, correspond to the decomposition of the overall variability in the response for a completely randomized design. We have the variation due to treatments, and we have the unaccounted for variation. And again, we have the degrees of freedom column listed just so that we can help remind us which row we're talking about here. But what we're really looking at here, the mean squares and the expected mean squares. So the mean square for treatments, MST, all right, is a random variable. And because it's a random variable, it has a distribution, and that distribution has a mean. Another way to say that is that this random variable MST has an expectation. And so that's what we're talking about here in these last two columns. The expected mean square for treatments and the expected mean square for error. And so let's look at this first row, all right, specifically at the mean square treatment. And let's look at the last two columns. Now, let's look down here at the last row first. I think that'll be easier. So let's look at the mean squared error, all right? Now, what this is telling us here, and we actually already know this first piece. We know that when we do a fixed effects analysis of variance, that the MSE, and specifically for a completely randomized design, we know that the expected value of the mean squared error is sigma squared, which again is the variance of the random error term in the model. All right, and this is why we use this. This is why we use MSE in the denominator of the F statistic. Okay, because regardless of whether the null hypothesis is true, MSE is an unbiased estimator of sigma squared. All right, what that means is that the expected value of MSE is sigma squared, regardless of whether the null hypothesis is true. And so we know that to be a fact for the fixed effects analysis of variance model for a completely randomized design. But it turns out that the expected value of the MSE is equal to sigma squared for a random effects model as well. Okay, so both for a fixed effects model and a random effects model, the expected value of the mean squared error is equal to sigma squared, which is the variance of the random error term, regardless of whether the null hypothesis is true. Okay, now, having said that, let's go back up and look at the expected value of the mean square for treatment for the two types of models that we're considering here, the fixed effects model and the random effects model. Now let's first look at the expected mean square for treatment under a fixed effects model. We see that the expected value of MST is not equal to sigma squared, but it's equal to sigma squared plus something. And if you look at this expression here, you'll see that it is necessarily positive because we're adding up things that are positive. The R sub i's, those are the replication numbers, the number of observations for each treatment. Those are obviously positive. And then we have these the squared treatment effects, the squared alphas. Now, again, the alphas themselves, some are positive, some are negative, but the squared values are always going to be positive. And so we're adding up positive values in the numerator, and then we divide by t minus 1. So this entire term here is positive. And so what this tells us, what this shows us, is that the expected value of MST will be greater than sigma squared if this term here is non-zero. Okay, now when will it be non-zero? It will be non-zero if the null hypothesis is false. Remember that the null hypothesis in a completely randomized design situation is that the population or treatment means are all the same, and that's equivalent to saying that the alphas are all zero. So the only way, because the sample sizes are always going to be positive, the only way that this expression can be zero is if all of the alphas are zero as well. Well, that's true if and only if the null hypothesis for the that's being tested by the ANOVA is true. In other words, the alphas are all equal to zero if and only if the population or treatment means are all the same. And so that is why we can say that the F statistic, remember we calculate the F statistic by taking the ratio of the MST over the MSE, and what we can say that that ratio will be close to 1 if the null hypothesis is true, because if the null hypothesis is true, MST will be, the expected value of MST will be sigma squared, and so it will tend to be close to sigma squared. MSE is always an unbiased estimator for sigma squared, so it will tend to be close to sigma squared. And so when the null hypothesis is true, then the ratio of those two independent statistics will tend to be close to 1. All right. However, if the null hypothesis is not true, then what that means is that the alphas, at least that the alphas are not zero, and so this term will tend to be, or this term will be positive, and so MST will be estimating something larger than sigma squared. And so then, in that case, the F ratio, MST over MSE, would be estimating something larger than 1. So that shows where that kind of intuitive description comes from when we describe what is going on in an analysis of variance hypothesis test and why we're looking for values of f that are greater than 1, quite a bit greater than 1. Now let's turn our attention to the random effects mean square, or the expected mean squares for the random effects model. And in particular, let's look at the expected mean squares for treatments under a random effects model. Now, the expression for the expected mean square is different than it is under the fixed effects model, but it has the same characteristic in that its expected value is equal to sigma squared plus something that will be positive in some situations and and then 0 in another situation. So when will this term be 0? Well, this first term in the product here, this is always going to be positive. It's always going to be non-zero. All right, so we can turn our attention then to this last piece. This will be 0 if and only if sigma squared sub tau, the variability associated with the random effects, is 0. All right, if sigma squared sub tau is positive, then this entire thing is positive, and so the expected value of the mean square treatment is going to be something bigger than sigma squared. So, what is being tested by the ANOVA F-test when we have a random effects model is the null hypothesis that sigma squared sub tau is 0 against the alternative hypothesis that sigma squared tau is positive. And so that is the difference between the two sets of hypotheses. So in a fixed effects model, the F statistic follows the F distribution, the central F distribution, if and only if this term right here is 0. And this is true if and only if alpha sub I is 0 for each of the i's going from 1 to t. The hypotheses that are being tested by the F statistic for the fixed effects model is therefore, and can be expressed in the following way. The null hypothesis being that the alpha sub i's are all 0 for I going from 1 up to t. The alternative being that alpha sub I is not equal to 0 for at least one of those treatments. Now, this is equivalent to the usual ANOVA hypotheses, or the way that we would usually represent these, at least the way we have been doing it up to this point. These hypotheses are equivalent to saying the null hypothesis that the means of the T populations are all equal. In other words, there are no differences among the treatment means, against the alternative hypothesis that differences do exist among the means. But keep in mind, this type of statement here, these verbal descriptions of what these hypotheses represent, as we look now at the random effects model hypothesis tests. So in the random effects model, the F statistic follows the F distribution, the central F distribution, if and only if sigma squared sub tau is 0. Remember, sigma squared sub tau is the variance associated with the random effect. Therefore, the hypotheses being tested by the F statistic for the random effects model is therefore given by the following. The null hypothesis is that sigma squared sub tau is 0. The alternative hypothesis is that sigma squared sub tau is positive. Now, these hypotheses can be stated in the following way. The null hypothesis would be that no differences exist among the treatment means across the entire population of treatments. The alternative being that differences do exist among some of the treatment means in the population of treatments. So if we scroll back to the previous slide, you can see the verbal descriptions, the interpretations of these hypotheses are very similar. Again, for the fixed effects model, the null hypothesis is that there are no differences among the treatment means in this particular experiment because they're fixed effects. Against the alternative hypothesis, the differences do exist among the treatment means for the treatments used in this experiment. On the other hand, for the random effects model, the null hypothesis is that no differences exist among the treatment means across the entire population of treatments, against the alternative hypothesis that says the differences do exist among some of the treatment means in the population of treatments. So again, we're getting a sense that we're making an inference not just to the treatments used in the experiment, but to the entire population of treatments from which the treatments that were used in the experiment were selected. Now, the rejection criteria of the ANOVA F test for the random effects model is the same as it is for the fixed effects model, so nothing changes there. In particular, for both types of models, the fixed effect and for the random effects model, the null hypothesis is rejected if the F statistic is greater than the upper alpha percentage point of the F distribution with the appropriate numerator and denominator degrees of freedom. Now let's look at the next question, estimation in the context of a random effects model. So the parameter associated with the random effects is the variance of those random effects, sigma squared sub tau, and we also have the variance associated with the random error term. So again, as we know, as we saw from the expected mean squares table, that the mean squared error is an unbiased estimator for sigma squared. And so we again get our estimate of sigma squared from the ANOVA table. And so that estimate, which again is denoted by sigma hat squared, is the MSE, the mean squared error, from that ANOVA table. Now we can use the expression for the expected mean square for treatments for a random effects model to come up with what is called a method of moments estimator of sigma tau squared. All right, and so it's just an algebraic manipulation to utilize or to come up with this, to utilize this estimate of the error variance and the value of MST as well. And so we have these two formulas, which the first one is always going to be correct. I've got two here because if we happen to have equal replication, right? So for example, if every treatment is replicated R times, then this simplifies to this expression here. So that's why we've got the two. But if this one will always work. Okay, and so this is how we get an estimate. If we happen to need it, we get an estimate of sigma squared sub tau. All right, and so we would denote the estimate by putting a hat on that, so sigma hat squared sub tau. And so again, this is how we can obtain an estimate of sigma squared tau using the mean square for treatment, the mean square error, and then values for the number of replications and the number of treatments. Okay, now let's look and see how to estimate the overall mean in a random effects model. So let's again look at the random effects model, y sub ij being equal to mu plus alpha sub I plus epsilon ij. In the random effects model, the alpha sub i's are random variables with expected value 0. The random error terms are random error terms with expected value 0. All right, and so the only constant here in this on the right-hand side at least, is mu, the overall mean. Okay, so what we're going to be talking about is how to estimate mu, that overall mean. Now, each sample provides an unbiased estimate of the overall mean. Recall that for each sample, I going from 1 up to t, the sample mean is given by, it's denoted by y bar sub I, and it's given by the average of the values in that sample. Okay, so each of these provides an unbiased estimate for the overall mean. Now, an unbiased estimate of the overall mean is also given by the overall sample mean, which you'll recall was given by this expression. I think we had a double bar on that. I'll have to fix that in the notes. Okay, but this is just the overall combined sample mean. All right, so so all of these quantities provide unbiased estimates of the overall population mean, mu. The mean, so let's talk about using an individual sample to estimate the overall mean. The mean of the sampling distribution of an individual sample mean, let's say that again, the mean of the sampling distribution, right? Because y bar sub I is a random variable, therefore it has a probability distribution. That probability distribution is called its sampling distribution, and so we're talking about the mean of the sampling distribution for that statistic. And again, we denote that by mu sub y bar sub I, and it turns out that is equal to mu, the overall mean. Okay, and so that implies that y bar sub I is, in fact, as we've been saying, an unbiased estimator of mu. Now, the variance of the sampling distribution of y bar sub I is given by this expression here. So sigma squared sub tau plus sigma squared over r sub I. So the variance associated with an individual sample mean in a random effects model depends not only on sigma squared, but also on the variance associated, the variability associated with the random effects themselves. Then once we have this expression for the variance, we can take its square root to get the expression for the standard deviation of the sampling distribution of y bar sub I, and so it's just given by that expression there. Okay, now, if we want to use the overall sample mean as an estimator of mu, let's justify doing that. So the mean of the sampling distribution of the overall sample mean is also mu, and so this implies that the overall sample mean is also an unbiased estimator of mu. Now, what is the variability associated with that overall sample mean? All right, well, the variance of the sampling distribution of y bar is given by this expression, so sigma squared sub tau divided by t, the number of treatments, plus sigma squared, the random error variance, divided by r dot, which you'll recall, that is the total or combined sample size. It's the total number of observations in the experiment. Now, once we have this expression for the variance of y bar, we can take its square root again to get the standard deviation of y bar, and so that would be given there. So these we have now expressions for the variance and the standard deviation, for the overall sample mean, and also for the individual sample means. Now the problem is that we don't know the variance components for these random variables. We don't know sigma squared sub tau, we don't know sigma squared. And so we're not able to calculate those variances and standard deviations exactly, right? So what we need to do is we need to estimate those variances and standard deviations from the data. Okay, so because these are unknown, the variance and standard deviation of the sampling distribution of y bar sub I cannot be computed exactly, but must be estimated from the data. Now this is accomplished by computing estimates of the variance components using the formulas given previously that we talked about just a few minutes ago, and the appropriate values in the ANOVA table, and then using those variance estimates in place of the unknown variance components that in the formulas we just looked at. And so, for example, to get the estimate for the variance of the sampling distribution of y bar sub I, we replace these variance components in the exact formulas with these estimates. All right, so sigma hat squared sub y bar I would be equal to sigma hat squared sub tau plus sigma hat squared over r sub I. Okay, and so again, let me just scroll back here. We're just replacing these guys right here with their estimates. Okay, and then once we have the estimated variance of y bar sub I, we can take the square root of that to get the estimated standard error. Right, so the estimated standard error of y bar sub I would be the square root of that expression. Similarly, we can do the same thing to get estimates of the variance and the standard error of the overall sample mean. Estimates of the variance and standard deviation of the overall sample mean are given by the following. So the estimate of the variance of y bar, so sigma hat squared sub y bar, is equal to sigma hat squared sub tau over t plus sigma hat squared over r dot. And then once we have that, then we can take the square root of that to get the estimated standard error of y bar.